so just generally technical sales, that sort of thing. I have a background in physics, quantum physics, in particular quantum computing, which isn't very surprising because D-Wave is a quantum computing company. So today I'm going to be going through a walkthrough of, it's going to be a 30-minute presentation, I believe. So I'm going to try to leave some time for questioning. And I'm going to be talking about the tech overview, kind of breezing through that, showing you a couple use cases, running a couple live demos on our computers. And yeah, oh, that's not good. Okay, well, I guess I'll just have to live with that. The basic thing about DOE you should know is that we are old. We have been around since 1999, which is positively ancient in quantum computing. And our tech has historically focused on one type of thing, but no longer. We now have two parallel streams. I'll go over. One other thing. I occasionally get really into my own head when I'm presenting. So if you guys have a question and you raise your hand and I don't see it, just yell. It's perfectly fine. I understand. So there are two major paradigms of quantum computing. They can be loosely described as analog and digital, but that's not quite accurate, but for the purposes of sales, that's fine. Let's see how efficient this is. So we have historically focused on quantum annealing computers. These are computers which were originally hard built to do optimization problems. And I'll talk about how they're doing them differently soon. So what is very unique about D-Wave is that we're the first quantum computing company to actually have people in production. We have a couple customers that are in production. We're not claiming that we have supremacy on these problems, but we're faster, cheaper, better, some combination thereof. We also have this type of problem. Generally, the type of things that we do with annealing, and although there's a caveat that I'll have at the end of this presentation, is discrete space optimization. If you don't know what that means, I'm basically saying you have some finite amount of resources you need to distribute to minimize or maximize something: money spent, time spent, employee satisfaction, something. And we also have some applications in AI and that we have rather recently been getting into. We're seeing some very, very promising results I can talk about. Gate model is the other paradigm of quantum computer that if you go online and Google and type what is a quantum computer, it'll probably give you an answer about gate model. This is the type of thing I did my PhD work in. This is the type of thing that Alice and Bob and Quantinuum and all these fine folks out here are working on. This is a more universal type of computation, but it's hard. It's really hard to build this type of thing. We estimate at least 5 years until it's ready for production use, and that is not a guarantee, but that's kind of our best guess. But we do believe that it is particularly going to be very useful for quantum chemistry and sort of continuous space problems. And there are very famous things like cryptography also will benefit quite strongly from gate model. Is there any questions so far? Okay. So one thing, I'm going to be focused on the annealing tech, but I will have some folks downstairs that can talk more about the gate model tech. So let's talk about optimization and kind of explain how this stuff does. You can think of optimization, as I said, it's something you're trying to maximize or minimize. And so you can think of that as a landscape. And I've drawn up a very simple landscape here. The landscape, the height represents the thing you're trying to minimize. So, like I said, dollars spent. Oh boy. Dollars spent. The computer functions as a hiker moving around this landscape. And for a lot of optimization things, you're just trying to build smarter and more clever hikers. It's not strictly true. I'm pretty sure he has caveats, but for general purposes, we'll go with that. So I have here a very, very simple landscape where the lowest point right here is the obvious solution to us, because we can see the entire landscape. But in reality, for realistic, interesting problems, you can't see the entire landscape. That's why you need optimization. So a greedy algorithm is a very simple type of classical algorithm. I think it's a little bit of a misnomer because it can be used effectively in some situations. But the basic idea of a greedy algorithm is, imagine that the hiker's head is bolted to some horrible accident, and they're bolted straight down, and they can only take in the information immediately around them. In jargon speak, it's making the optimal decision only using your local environment. So the hiker knows I'm looking for the lowest point. I got to go down. But I can only see what's right here. So what's the steepest direction down? Northeast. All right, what's the steepest direction down? North. Repeat, et cetera, et cetera. The down, it's efficient to go down, but the issue is that you only know how to go down. you can hit a minimum pretty easily, and you can get caught. So that's a very simple one. A slightly more complicated one, simulated annealing, is effectively you give the hiker some probability of taking a step upwards. So the way I've animated this, it's kind of a jiggly hiker. And the idea is that they are able to step out of some minima. They might, depending on how jiggly you make them, it might be a little more difficult to go over some other other barriers, but it's a very clever idea, very common type of thing. I also want to stress, because this is important and a distinction and an unfortunate quirk of the English language. Simulated annealing is not simulated quantum annealing. They're different things. They're two branches off the same tree as opposed to one being a branch of the other. Okay, now I'm going to go to quantum annealing. And the analogy begins to break down, as does many things when you're trying to make analogies about quantum mechanics. So first off, there are two things. Note that the landscape, which again represents the problem you're trying to solve, is different. It's a very simple, shallow bowl. Two, notice the hiker is stretched. It might be more apt to think of them as a cloud across the landscape, actually, than a hiker. And I'm just going to play the animation. So what we're actually controlling on our machines is the landscape. We are returning the landscape from this simple one to the more complicated problem we wanted to solve originally. Right? And there's this trick of quantum mechanics, depending on the textbook you read, it's either called the adiabatic theorem or adiabatic approximation, but this encourages the hiker's cloud to coalesce, and it further encourages that the cloud coalesces near or at the lowest possible point. This is how quantum annealing works at the core level. And I recognize this is kind of weird. Does anyone have any questions at all?
Do you know the origin of the word annealing for this application?
Welding.
It is welding?
I believe so, yeah. The idea is basically that you have a temperature thing that you're changing up and down, and then, like with annealing for like welding, it's something, what is it? You reheat it up so it can cool down into a stronger state, right? Kind of the same idea.
Thank you.
Yeah, the analog for temperature in simulated annealing is the jiggliness of the guy, and the analog in temperature for quantum annealing is effectively the percentage of bowl versus complicated shape. Is the temperature analog. Although you do have to actually care about real temperatures as well, which is cool.
When you say the quantum cloud coalesces, do you mean it condenses into like a specific state?
Yeah, it'll go down to a computational basis state, like a bit string. Yeah. I find that sometimes people want to, depending on the audience, that can be, they can go right over their head. So, but if you need me to be any more technical or less technical at any point, don't hesitate to ask. And I will be downstairs today and tomorrow for questions as well. Okay, so how do we actually realize this? Our current best machine for this is the Advantage 2. This is a flagship machine. I don't have a picture of it right here for some reason. I forgot to put in a picture. But imagine a black box about 3 meters by 3 meters by 4 meters. Okay, the actual chip itself is like roughly the size of my thumb, or thumbnail. But there's a lot of like shielding and anti-vibration stuff and cooling that has to go into this. There's a lot of numbers on this page. The basic thing you need to know is that we were able to build a machine with over 4,000 qubits, which is an order of magnitude beyond some of our competitors, 2 orders of magnitude beyond most of our competitors. And each qubit is directly wired to 20 other qubits, which might not sound too impressive to some people. Let me tell you, that's an impressive number. And then there's a whole bunch of other things, like it doesn't use that much power, about 12.5 kilowatts, which I thought was roughly the power of a house. I was corrected. It's more than a house, but it is probably about 2 houses. So it's not like a supercomputer type thing. You don't need power. You don't need enormous power stations to run this. So this is all I was prepared to go in for tech. I was going to go more into demonstrations next. Is there anything? Does anybody know if that guy was videoing me or taking pictures?
I think it was pictures.
Okay, good. Because I was like, I come from, this is Taran knows, I come from lobsters and seawater, and I swear sometimes. So like it's that's a lot scarier when you work for a company and you're being recorded. So I'm going to go over 2 demonstrations. One is sort of a more businessy demonstration, and they're both for businesses that we work with. One is more businessy, one is more cutting edge sciencey. In fact, I would almost characterize it as bleeding edge with our tech. They are very different. I'm going to show you, I can't show you the actual code that they're running for IP reasons, but I can show you something similar. So Ford Otosan, Ford, they make cars. This basic problem is job shop schedule, in a sense. So the idea is that you have machines that can do jobs, you have a bunch of jobs that need to be done, and you want to try and minimize the amount of time it takes to do those jobs, the make span, by assigning jobs to machines. You think this is easy, and in some cases, if you have like 3 machines and like 10 jobs, it's not the worst. But as it scales to a factory, it suddenly becomes incredibly difficult. So Ford Otosan came to us and they said, "Hey, this isn't our current production tool isn't really cutting this. Can we try something with you?" The actual thing they were doing was bolting car doors onto cars and in a specific order. And you'd think it would just be like, do all the blue sedans, do all the blue vans, do all the red sedans, do all the red vans. No, it turns out that there's different changeover costs and stuff, and it actually becomes quite complicated. It almost would, to someone who's not really trained in this, the final result will look almost random, but it is highly optimized. And that's the reason why we do optimization in the first place, right? Is that intuitive answers are no longer working efficiently. Now, we were able to increase the runtime. We got down from 30 minutes to do 1,000 vehicles, to schedule 1,000 vehicles down to 5, less than 5, which is good. But I think that this slide kind of misses the punchline that we got from these guys. So when we were working with Ford Otosan, they said, "Hey, we actually aren't solving the whole problem. We weren't able to get our machines to incorporate their tools they were using, which are commercial tools, to incorporate certain constraints that made their factories safer and better for their employees." And so they just kind of had to put it out, do some post-selection, hope it worked. And we were able to incorporate these constraints and create a safer environment, basically. The actual thing that they were having trouble with is if you look at the graph of like manual intervention required over time, so like humans helping the machines, it was a big sine wave. It was very deep. And these transitions from like, everybody's doing stuff, no one's doing stuff. Everybody's doing stuff, and no one's doing stuff. These transitions are not good. People don't want to be doing that all day at work. If there's tons of changes all the time, it can be dangerous in a factory setting. That cost is measured in fingers. It's careful. So we were able to make that incorporate rules that make it a nice steady output. A nice steady, moderate amount of work throughout the day. That was cool. So now I'm going to show you a similar demo. As I said, I can't show you the actual code they're using, but I can show you flow shop scheduling. So I mentioned job shop scheduling. Flow shop scheduling is very similar, except there's an order to it. So I'm going to run this while I'm talking on a small example problem. You have a bunch of machines, you need to do jobs, but there's an order to the job. So in the example they give up here, you can see in the top right, it's like lift container, open container, unload cargo, reload cargo, dispatch truck. In this type of context, it's difficult to switch the order up in those. Like you can't load the container when it's still full. You need to unload it first. You can't unload the cargo before you open it. With pure job shop scheduling, order doesn't matter. I think of it as like if I was building a guitar, like I can bolt the neck on before or after I'm wiring up the pickups. The order doesn't really matter. But baking a cake, I can't put the eggs in after I put it in the oven. There's an order to it. So I just ran a live demo with our quantum hybrid tech and a classical solver called Highs, and I'm going to show you the answer here. We're going to try and find the minimum make span, so the total time it would take to do all these jobs. And I picked a very simple example with only 5 different types of jobs, but 12 machines. So for the classical results, we have a make span of around 8,300, which whatever time units are here. And for our quantum hybrid, we have around 7,300. So you can see there's a 10-ish% increase in speed, or in efficiency. And again, as I said, they look kind of random to the untrained eye, but that's why we need optimization. That's why optimization math exists. Now, let's crank it up. Let's make it a little harder. So now I'm going to have 10 different types of jobs, 20 machines to distribute. And this will take a second, I apologize. It's a live demo and the Wi-Fi is not 100% perfect, but that's perfectly fine. It's better than, I was at a conference recently and they were like, oh, we paid for Ethernet cable, and then it turns out the Ethernet port on the laptop was busted. And as you know, for conferences, they charge a lot. So the classical results, because those are running basically locally, those should return, a little bit earlier. So let's check. We have make span of 1992, hybrid 1566. All right, so we're getting a better results, a little more than 10%. And this is a trend that we tend to see, especially with our hybrid tech, is that for small problems, we're maybe a little bit better, a little bit worse, the middle, whatever. And then as the problems get more and more complicated, more realistic, we tend to start to pull ahead. So I can do a sort of extreme example. I can pump this thing all the way up to 10 different jobs and 30 machines to distribute to. And in theory, as I said, this is a live demo, and this is a heuristic solver, so it might not return what I think it's going to return, but in theory, it should return something fairly dramatic.
Ken, is the hybrid optimization the most optimized?
No. Well, wait. I'm going to double check. I know exactly what you're asking. Are you asking, does it achieve the optimum?
Yes.
No. So none of our tech is guaranteed to return an optimal solution. It's all heuristic. I'm sure that my theory team would kill me for saying it like this, but basically, like, there's the type of analog quantum computing that always returns, that's the best optimization solution. It's called quantum adiabatic computing. That has some interesting bottlenecks that are problematic. So quantum annealing tech basically says, screw this, we're not going to guarantee that you get the best solution. We're just going to go a little bit faster and jump over these bottlenecks, essentially. And in doing so, we become a heuristic solver, but we're able to avoid the big blow-ups.
One way to think of it is it's asymptotically admissible. You follow?
Yeah, I do.
Okay, so asymptotically, but not guaranteed unless you have an infinite amount of time.
Yeah, and a perfect machine.
The perfect
It's a perfect machine. But that's for adiabatic computing.
Right.
Yeah, the annealing one is slightly different. So now let's check the hybrid results. We have a make stand about 2100, and for the high solver, nothing. It failed. It's this problem. I only gave it 10 seconds, but it couldn't find an answer. And we found an answer in 10 seconds. And this tends to be the niche that we occupy, is we're not necessarily, when you're not necessarily looking for the best possible answer, but you're looking for a workable answer quickly. Which tends to, often in things like logistics, it comes up like, oh, something just changed, I need to adapt. I need to adapt my plan. And suddenly, it doesn't matter if you have the absolute mathematically perfect solution, you just need to get those trucks in a row.
So were you making a live call to a quantum computer just now?
Yes, sir. Yeah. Now, I'm going to go back to my presentation for a minute, and I'm going. So this next use case is very, 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 very different. It's not even really an optimization problem. It's weird. So we were working with a company called Shinogi, Japan Tobacco Farm. And their niche was they were trying to create small medicinal molecules. Okay? So small medicinal molecules are easier for some things, like they can pass through cell membranes more easily for certain, which is important. So they were looking to make new medicinal molecules. And there were there was more metrics, but there's 3 metrics that are going to come up later that I'll talk about. So they were looking for smaller, the smaller the better. More, I actually don't know how to pronounce this. If anyone does know how to pronounce it, because I only ever read it. It's either lipophilicity or lipophilicity. Lipo? It is lipo? Okay. The molecules are more comfortable around lipids, like the phospholipids around a cell. And there was a supermetric which unfortunately called QED, which for physicists means one thing, but for them it meant qualitative estimate of drug readiness. As I said, it's not an optimization thing. They are running the machine in a way that it was not originally designed to do. And they found that across these 3 metrics, they improved something like 10 to 30% compared to the tools they were using before. And they actually just published this. So this is all open source. Like, they published it about a month and a half ago in arXiv. So this is it's pretty cool. Yeah, let me tell you, I was waiting for that because I didn't know what I could say publicly until they did that. We've had some variations of this before. There's some people that there's some people from Riken and UTokyo that were working on this, and they actually got to the wet lab stage. They actually synthesized some of the molecules, and they synthesized 4 of their molecules. One of them didn't work. 2 of them worked fine. The 3rd one worked, but also would have killed you. So worked is debatable. These guys haven't gotten to the wet lab stage yet, but it's really cool because it's our first not really they're not in production yet, but it's our first major industrial scale generative AI use case. So I can't, as I said, I can't show you the exact code, but I can show you something that is very, like under the hood, very similar to what they're doing. And we're just going to do image generation for the MNIST data set, handwritten digits. So I'm just going to run that right now. While I wait, I'll pick let's do 40 epochs. I'm not going to train it right now because it has to make a lot of calls to the QPU, and the cloud latency, that'll be like 20, 30 minutes. That's not a good demo. But I can submit the jobs with pre-selected settings. The basic thing that's happening here is there's a type of network called a Boltzmann machine. And the equations that govern a Boltzmann machine are the same equation, or informationally equivalent to the equations that govern the QPU, the quantum processing unit. So we can use the QPU as a Boltzmann machine. Pardon me. Nope. Sorry. Somebody from here. So the QPU, we will adjust the setting. Oh, I'm sorry. Let me back this up. So what we first do is we use an encoder. So we take these handwritten digits and we compress them and encode them into a smaller size that can be represented as a bit string, zeros and ones. And this training data set will have a probability distribution of the various ones and zeros. And then what we do is iteratively change the settings on the QPU until the sampling from the QPU is the same distribution as the training data. Okay? Then we just have the opposite of the encoder, the decoder, and when we can then take samples right out of the QPU, plug into the decoder, and they should, in theory, look quite a lot like the input data, the training data. But we don't want it to look the same. That's the point. We want it to look almost the same. In the drug case especially, because they're trying to create new molecules that are like older molecules. They have certain similar properties, similar substructures, but not quite the same. So I can walk through some on the left we have the actual generated images, and you can see that these are generally recognizable. This is not freshly trained, so there's going to be some weirdness, like that. Well, that's a 2. That one up top right could be a 3 or an 8, but these are recognizably numbers. On this side, we're kind of doing something different, where these are actually training data on them, and then this is plugged in through the entire system, and it should look roughly the same coming out, right? And generally, there's agreement. There are occasional mistakes, like this 8 and a 9, that can come up a little bit. 1s and 7s sometimes get messed up. That's an interesting one. It lost the middle bit there. Huh. But you can see it's generally recognizable, generally works. And I can tell you that the code that's running underneath this is very similar, very, very, very similar to what's being done with Shinogi, those guys. It's just a different type of data set. Any questions about this one? Yes.
Is there a way to integrate which parts of, for example, the starter drug is more important?
Yeah, actually.
versus other parts?
Yeah, there are. I'm sure there's a term for it. It's essentially that you just hardwire those qubits to have certain values, and it will bias. It will bias the system to prefer things that work around that small substructure, and then build off of that in a way. Yeah. Someone else had a hand over here, I think?
Same question.
Oh, same question, yeah. It's pretty cool. It was really like, to be perfectly honest, when they told me like, hey, we're going to try this, I was like, sure, okay, we'll give it a shot. And it just really worked, and it's a testament to, in particular, this Mohsen Rahmani, who on our team, and Mohammed Amin, who did a lot of work on this. And they used the machine in a way it wasn't meant to be used, and they found it works exceedingly well. And that's very impressive work by them. All right, so.
Just clarify, you said there are 2 steps, right? Was the first part the discrete variation autoencoder, and the second part was the Boltzmann, or? Yeah,
the first step is the autoencoder. You have to encode everything down and compress it into a space that the QPU can read. We found that the best thing is about a couple hundred qubits, I think it was on the order of like 400 qubits. Was roughly the space that it seemed to perform very well with. And which also means we can submit multiple jobs to the QPU at the same time because it's only taking up a little bit of the QPU. Makes things way more efficient. And then the QPU part, this is all classical, this is all classical. This part where we're changing the settings on the QPU to try and get the same output, that's the quantum part.
But in encoding is similar to embeddings, and what is this different?
Oh, it is a different. Ultimately, embedding will have to happen in the space in between here and here, but no, encoding is just dropping it down into a compressed space. Yeah, with hopefully not too much loss, and then we experimented with different levels of compression and encoding. But yeah, good question on the embedding one. Yeah. All right, I think I have about 5 minutes left, so I'm gonna just, which is actually almost perfect because this is my last slide. So if you want to get involved, there's a few ways. I didn't put training on here. I should have. We do training. Come see us at the booth. I'll be here today and tomorrow. I'm very happy to talk about whatever you guys want to talk about. I think we also have some booths up here. We have examples of our annealing chips and gate model chips. There will be people from both teams if you want to talk either one. You can also access us with Launchpad is sort of the easiest access. If you have an idea, it's free. It's one time only. You get 3 months of access, but you have to apply for it. You're not guaranteed to get it. Launch is the exact opposite. It's white gloves, like everything. Like you have to pay for it, but we will do everything from light advisory services to hands-on keyboards building the thing for you. We get the most success with that one because we know our tech very well. And then there's a sandbox environment as well, which is the quantum cloud service. We sometimes call it QCAS for quantum computing as a service. But those are the general ways that people interact with us, other than training. Yeah, I think that's all I have, and I have a few more minutes left for questions.
So we talked the second use case, was the way you phrased it was training an LLM and transform an LLM. So is it actually like an optimize some kind of cross function over multiple steps?
It's sort of optimization, but it's weird. It's what you're trying to do is normally with annealing, what happens is you're given the landscape and you're looking for the lowest point. In this one, we're actually looking for the landscape. Essentially, you're given something what the landscape should look like, and you have to find the settings on the QPU that return the landscape. Yeah.
Maybe the element of the landscape is the sense of weights and biases. Are we playing with that to get training in some interesting ways?
I believe that is correct. Yeah. Again, I'm gonna level with you guys. AI ML, not my strong suit. Quantum physics, cosmology, pretty good at those. But yeah. But that is generally correct.
I have a question from like a business perspective,
Yeah.
like the Ford example that you gave. So what, like in terms of like, what does it look like? How many staff do you need to kind of get involved? Do that kind of work with Ford? How long does it take to get to that point? And who do you hire like to do that kind of
Oh yeah, so we've worked really hard to try and make some of our stuff so you don't necessarily need a quantum expert, but you need like an optimization expert. If you want a quantum expert, you can get really nitty gritty, but so usually like an optimization person is something good to have on hand if you want to try and integrate it. It does occasionally take a while. We usually expect a full-scale proof of concept where we like try and build something that could theoretically run, not just a test case, is usually on the order of about 5 months. That being said, occasionally people do it in a week. It's not very common. It's happened like 3 times since I've been here. I think twice actually that I can think of. But it does happen. Some people just get it. But so usually I budget a few months to build it. It's not so much that you need to hire new people, it's that you need to bring in the right people. So one thing that's really important is making sure that if you have a problem, whoever owns that problem is talking to us. You'd be surprised at how many businesses don't do that. Where they come in and they say like, oh, like this is Jeff's department, but like you don't need to talk to Jeff. Like, no, we need to talk to Jeff. Like we need to know what you actually need.
Why does that surprise you?
I think I have more faith in people than I did. I don't know. I came in wide eyed. It was but it is something we've had to do. It's just you don't necessarily need to hire new people. You just need to bring in the right people, and we can help train you up. In fact, one of our customers, we built their first application. They basically watched us, and they built their second application.
On the optimization side, is the API interface do you have to define like a mixed digital?
It's kind of mixed. We have different tech you can use. So one will take something that's a lot like a mill. one, our better one, does not. It takes a little bit of a learning curve, but it is insanely powerful. It is frankly a lot better than we thought it was going to be. I mean, it's